Hello everyone. Welcome to week 10 of NPT live mentoring sessions. I hope I'm audible to you. Okay, so today I'm not going to pick up one specific topic. I'll be going to discuss some random problems from GATE 2014 specifically, and maybe one or two from GATE 2017. Okay, so it will be from structural analysis specifically, if you want to know. Then let's start with the first problem, which is GATE 2014, set 2, question number 12. If you have any doubt, you can stop me anywhere, anytime, okay? So it's a very simple problem in which we need to find the static indeterminacy of a two-span continuous beam with an internal hinge. So it's a two-span continuous beam with an internal hinge. So in beam, it's very easy to find the static indeterminacy. So in general, what is static indeterminacy? Static indeterminacy is simply, if you want to know the formula, so static indeterminacy is the unknown which we are not able to find out using equilibrium equations, right? So static indeterminacy is unknowns minus equilibrium equations. So that is the degree of static indeterminacy, right? In beam, we can find out very easily. So what we will do, we know that this, or let's start with the simply supported beam here. So we know that a simply supported beam is a determinate structure, right? A simply supported beam is a determinate structure. Why is it's a determinate structure? Because we have unknowns 1, 2, and 3. There are three unknowns. Three unknowns means reaction 1, reaction 2, and reaction 3 here. Because it was a hinge support here and it is a roller support here. So two reactions at the hinge support and one reaction at the roller support. So in total, three unknowns. And how many degree of equilibrium, how many equations of equilibrium we have three equations of equilibrium. So if we find out the degree of static indeterminacy for a simply supported beam, it is 3 minus 3, that is unknown, minus equilibrium equations, it equal to 0. So we know that this beam, which is a simply supported beam, it is always a uh, yeah. So simply supported beam will be a determinate structure. So we know that, right? Now what we will do, whenever we will add one support in this structure, okay, if we add a support in this structure, it will increase the degree of static indeterminacy. And whenever we add a hinge in this simply supported structure, it will reduce the degree of static indeterminacy by 1. So it's simple to solve, right? So if we in this beam, simply supported beam, if we add one more support here, so degree of static indeterminacy, earlier it was 0 for a simply supported beam, but now it will become 1, right? If we add one more support, it will be 2, right? So that's how the degree of static indeterminacy vary. But now if we add one internal hinge in between, so it will reduce by 1, so it will be minus 1 now. So degree of static indeterminacy in total will be equal to 1. So that's how you should proceed for a simply supported beam, right? But now in our structure, if you want to find the degree of static indeterminacy, we'll proceed in the same way. So this is a simply supported beam with an overhang here. So this is simply supported beam with an overhang initially, right? So now here at this point, it is a statically determinate structure, right? Now what is happening? We are adding one support here. So what will be the degree of static indeterminacy now? Degree of static indeterminacy is becoming 1 now. And now we have added one hinge here also. So now hinge will reduce the degree of static indeterminacy by 1, so it would be minus 1. So finally for this structure, what is the degree of static indeterminacy we are having? 0. This means that the given beam is a statically determinate beam, that is degree of static indeterminacy is 0. So answer here will be 0. Okay, I hope there should not be a problem for the beam. For the columns, there are specific there are for sorry, for frames, there are specific formulas which you need to follow, because in case of frames, you cannot look at every joint and find the unknowns, and then find the degree of static indeterminacy. So it's better to use the formulas for the frames, but for the beam you can easily identify the degree of static indeterminacy. If there are any doubts, you can stop me. Okay. Yeah, so now this question was very easy. The answer is 0, right? It's a 1 mark question with no negative marking. Yeah. So now we have one more question which is a little bit tricky, you can say. It's question number 32 of GATE 2014 set 2, right? So here there's an assembly which consists of a beam and this member PQ. Okay. So we need to find the axial load in the member PQ for this assembly. So it's a fill in the blanks type of question. There are no options. So we need to find the axial force in member PQ, right, for this loading. So how to proceed with this type of questions? Okay, since we need to, so this is a beam here. This is one member PQ, and there's an hinge also here. There's an internal hinge at the at Q. Okay, so let's find out the axial force in member PQ. So this is the problem. So let me draw. So what we will do, we need to, since we need to find the value of PQ, we will separate the structure from here, and let's draw kind of free body diagram for this. Okay, so this is the beam we have. Let me shift downwards. Yeah. And we have this member PQ, right? I've just separated these two members. So here it is P, here it is Q, this is Q, and this is R. So why I have separated it from Q only? Because I needed to find the value of FPQ. Whenever we separate a structure from somewhere, what we do? We release the forces there, right? So here, this, I have to release the force from here, and this force is FPQ, and here also similar force FPQ is there. Okay. Another, let me draw another loading. This is 160 kilonewton, and there is no other loading except this. Okay, I hope it is okay. So I've just separated this structure from here, and I have drawn these two separate structures here. Okay, now I need to find the value of FPQ now. Okay, so now we will use one compatibility condition. So I have separated it from Q, but I know that in actual structure this Q portion is attached. So what compatibility condition we can use here? The condition which we can use here is Q will have to deform equally. Like whatever is the deformation in this part, this Q, that is the Q which is attached to this PQ structure, the same deformation should be there here also. Why? Because in actual structure these two are attached. Okay, so the compatibility condition which we will use here is, that is deformation Q1. So let us call the deformation in this member be delta Q1. Okay, the deformation of this point Q for this structure, let's call it as delta Q1. For the second structure, that is this beam, let us call the deformation at Q be delta Q2. Please look at it very carefully. Okay, what I am doing, I am saying that this Q here and this Q here will deform equally, right? Why? Because they are attached in actual structure. So that is a compatibility condition I'm going to use. So I'm saying the deformation at this Q, let's call it delta Q1, and deformation at this beam, the Q point at this beam, I'm calling it as delta Q2. So what is the compatibility condition I'm going to use here to solve why I'm using this compatibility condition? I'm using this compatibility condition because finally I have to find the value of this FPQ, and without using the compatibility condition I cannot solve this problem because it is an indeterminate problem. Okay, so what the compatibility condition I'm going to use, delta Q1 is equal to delta Q2, that is the deformation of point Q in structure 1 is equal to deformation of point Q in structure 2. Why is it so? It is so because these two points are actually attached in the original structure. So that is the compatibility condition, right? So this is the condition I'm going to use, and using this condition I'm going to solve for the value of FPQ. I hope there should not be any problem till this point. Okay. Now, what will I do? I'll find this delta Q1, I'll find delta Q2, I'll equate these two things, and from that equation I'll find this FPQ. But before that, there's a thing which is not given in this question, which they should have mentioned. The thing here is they should have either give so the thing yeah, so it is that they should have given the axial deformation can be neglected. So why this thing is required? This thing is required because here I'm going to equate delta q1 with delta q2. So delta q1, how will what is delta q1 actually? So if I'll remove everything, so what is delta q1? How will I find delta q1? Delta q1 is nothing but PL by AE. That is how you find the deformation in an axial member, right? Whenever there is a bar and there is an axial load applied to it, in this case it is FPQ. So if I write FPQ here, how will you find the deformation? You will find the deformation using this formula, right? PL by AE. Here in this case, P is FPQ. Length is length of this bar and divided by AE. Okay, so delta q1, this delta q1 I require to solve this problem, but they haven't given us the value of a, e, or anything I. Neither they have given the dimension of this bar PQ so that I could calculate the value of this AE. So all these things, without all these things I cannot find the value of delta Q1 here. So another thing is that whenever in a structure, the axial deformations, whenever there are axial deformations, they are very small as compared to the flexural deformations. Okay, so in this beam, in this part of the beam, there are flexural deformation. Flexural deformations means the deformation due to bending of the beam. Okay, so there will be bending of this beam, and this part PQ is deforming axially only because there is only axial force applied to this part PQ. So in any structure, the axial deformations are very very small as compared to the flexural deformations. So this another reason where we can say that we have to neglect the axial deformation. So this part is very important for this problem. Okay, so they should have mentioned in it in the question that you have to neglect the axial deformations, but if they haven't mentioned, then we have to assume that the axial deformations are very small as compared to the flexural deformations, therefore we are neglecting it. So this thing will be helpful to us in solving the problem. How, we will see. So now we are assuming that the axial deformations are very small as compared since the axial deformations are very small as compared to the flexural deformations, so we can neglect them. So it means that delta q1, in the compatibility condition we have this equation, right? Delta q1 equal to delta q2. So this was the equation, right? Since we are saying that axial deformations can be neglected, so we can write that delta q1 is 0 here because we are neglecting the axial deformations. Since delta q1 is 0, so the compatibility equation will now become delta q2 equal to 0. So we need to solve this equation now in order to get the value of FPQ. So this question is a little bit tricky. Okay, so this small things you should keep in mind for this problem. Okay, so these are some of the different problems you can get in gate. Okay, yeah, that is right. Either they can write that member is inextensible, that is the same meaning. Inextensible means it cannot extend axially. So it cannot extend axially means this point Q cannot move anywhere. Okay, so it is as good as a support. Even if they remove this member now, if they remove this member and draw it like this, So it is same, right? Because this point q this pq is kind of a support now, it cannot move actually. Okay, but just to confuse us, so they have given it like this. Okay, if they want us to take into account the axial deformations also, if they do not want us to means neglect the axial deformations, then they would have given us the value of a or e. Okay, a and e, right? Then because then only we can find out this delta q1. Because other, if they have not given us the value of a and e, we cannot find the value of delta q1. But since they haven't given us the value of a and e, so we can assume that axial deformations are very small as compared to flexural deformations, and therefore we are neglecting it. So this has made our problem a little bit simpler. Why? Because now we can have to use only we have to find the value of delta q2, and we have to put it to 0, and from that equation we can find out the value of fpq. Okay, so in this all this thing, do not forget that we need to find the value of fpq, right? So now our compatibility condition has become delta q2 equal to 0. We will simply solve this equation and we will find the value of fpq. Now our entire focus will only be on this beam part. Okay, because this pq part is not deforming, so we are neglecting it. Okay, yeah. So now I am drawing this beam part because that is the only thing which is important now. Yeah, so this is the beam in which we have this 160 kilonewton load here. Another thing here is this part, which is fpq, which we have released. Okay, if you remember. So now this is delta q1 is 0, so delta q2 is also 0. So our equation which we need to solve is delta q2 equal to 0. So we need to find the value of delta q2 and we need to put it to 0, and from there we can find the value of fpq. Now this is the structure which we need to solve. So we can, for simplicity in solving, we can write that this structure is a sum of these two structures. Okay, plus I can make it like this. Now this structure is the sum of this structure number 1 and this structure number 2, right? If I, so what will I do? I'll find, this is q point, so I'll find delta q from this structure and delta q from this structure, and I'll add both of them to get the value of delta q2 finally. Okay, so let's call the deformation of point q here as delta 1. Okay, and the deformation of point q here as delta 2, right? Now I'll find, so what will be delta q2 now? Delta q2 is delta 1 plus delta 2, and in total it is equal to 0. So it is 0. So this has become our final condition which we need to solve. Okay, so in structures it's very common that you need to break these structures into different parts in order to for simplification and analysis. Okay, so what we will do, we will find delta 1 and find delta 2. So delta 1 and delta 2 are very easy to find now. So let's find delta uh, 2 first. Okay, because it's easy. So let's find delta 2. So what is delta 2 here? So this is our structure. Delta 2 is fpq here. So delta 2, how will I find delta 2? From the standard deflection formula. You know, right? Whenever there is a cantilevered beam and we have this load P applied to it, so what is the value of delta we get from the standard deflection formula? The value of delta we get is PL cube by 3EI. This is the standard formula, right? So here also it will deflect like this, and this delta 2 will be equal to f, here p is fpq, right? Fpq, what is the length of this beam? 4 divided by 3ei. This is the value of delta p. Simple. I've just used the standard deflection formula. Now let's find delta 1 also. So this is delta 2, right? Now let's find delta 1 also. So this is our structure. Here I have 160 kilonewton here, right? So now I need to find delta 1, that is deformation of this point Q in for this loading. So how will this beam deflect under this loading? It will be curved till this loading and straight line after that. I have discussed this problems a lot of time, right? Curved till the loading and straight line after that. Okay, so I need to find this value of delta 1. Okay, so delta 1, what will be delta 1? This deformation, right? This deformation here, that is will be equal to deformation at this part, and plus theta times this length. So this is the standard way in which we find the thing, right? I've discussed it a lot of time. I hope if you have any doubt in this part, now please let me know. Okay, so delta 1 will be equal to deformation under this 160 kilonewton load, which is PL cube by 3EI. So P is 160, length is this length is 2 meter, PL cube divided by 3EI, plus this was this part, right? And now theta times L will be this part. Theta times L will be this part. So what is theta? How will you find the value of theta whenever there is a uh, point load here? So theta is PL square by 2EI. So this is how you calculate the value of theta, right? Please remember these standard deflection formula. You'll see they will not never ask them directly, but they have asked them in this question, okay? Because without them you cannot able to solve this problem. Okay, so now it is theta times L. So what is theta? Theta is PL square by 2EI. So PL square by 2EI multiplied by length. This length is also 2. So it is 2 here. So from here we get the value of delta 1 as 4426.67. If you want, you can solve 640 divided by EI. So in total, the value of delta 1 which I am getting is 1066.67 divided by EI. We do not need to put the value of EI, and it is also not given to us. So this is the value of delta 1 and delta 2 we got. So now, yeah, so now we can put this in our compatibility condition. So what was the compatibility condition we had? We had delta Q2 equal to 0. So what is delta Q2? Delta Q2 is delta 1 plus delta 2 equal to 0. So what is delta 1? Delta 1 is 1066.67 divided by EI. And what is delta 2? Delta 2 is this. So this delta 2 is in upward direction. If you see, this is in upward direction, so I'm putting negative sign here. Okay, so you can put this negative sign here. This is downward deflection I'm taking as positive, and upward deflection is negative. So it's minus FPQ 4 cube divided by 3EI equal to 0. From here we can get the value of FPQ as, if we solve it, we'll get the value of FPQ because EI will get cancelled, and if we'll solve it, you'll get the answer nearly equal to 50 kilometer. So this is the final answer. You see, this problem requires so many things you should know. Okay, so first thing you should know is, if they haven't given the value of A, it means that I cannot find delta Q1 here. It means that they want us to know that the axial deformations are, since they are small, so we can neglect them. So the first thing you should keep in mind. Second thing you should know is, are the standard deflection formulas. Without the standard deflection formula, it will be very difficult to solve this problem in a conventional way. Okay, so another important thing which I like stress over again and again, please remember that table in which those standard deflection formulas are given. And third thing is practice, because without practice you won't be able to know that where to apply what thing. Okay, so what things are needed to be applied in this question. So are there any doubts? So whenever this type of structure in which different loadings are given, you should separate those loadings and finally add the final thing to get the answer. Okay, is there any doubt or should I proceed? Okay, you should practice this. Okay, please practice this type of questions. Okay, because they are very common in GATE. Okay, so it is a little bit complicated question, maybe. So let us do one easy question. Okay, this is one easy question. If you want to try, you can try. This is a GATE 2017 question, question number 32. It's a 2 mark question, but it's a very, very easy question. Okay, so in this, you have given three prismatic beams with support, with clamped supports at P, Q, and R. So these three beams are given with different loading. In the first beam, we have this point load at the end. In the second beam, we have this UDL, and the third beam, we have only this moment. You are given the value of modulus of elasticity, the moment of inertia, and so they are asking the correct comparison of the magnitude of shear force, bending moment developed at the supports. So what we need to do, we need to find the value of shear force and bending moment at the support. For example, shear force at this support P, we can call it SP, and the bending moment at this support P, we can call it MP. Similarly, we can call the shear force here at SQ and bending moment as MQ. Okay, we can call shear force here at SR and we can call bending moment here as MR. Okay, so you just need to find the value of shear force and bending moment at for all the three beams at the support location, and then and finally you need to compare these values. So A, B, C, D, four options are given to us in which the comparison is given for this shear force and bending moment for all three beams, and then you can choose the correct answer. Okay, so can you tell me what is the value of shear force? What will be the value of SP and MP? It's very easy to get the value of SP and MP, right? So it's a very easy question. Finding out shear force and bending moment for these three cantilever beam is not a very big task. So if you can, okay, so I'll do it for you. So I've already done it. There's an 80 Newton load which is applied, right? So I can draw the free body diagram here. Okay, so I'm drawing the free body diagram if you say. Yeah, so here we have this 80 Newton load. So at the support, what will be the load? Load will be upward 80 Newton, right? In order to balance the vertical equilibrium. What will be the moment at the point P? The moment will be 80 multiplied by this length 8, right? And the direction will be like this. And the value 80 multiplied by 8 is 640 Newton meter. Very easy to solve, right? We have got the value of SP and MP within seconds. Now for this beam also we can find the value of, we can draw the free body diagram similarly. Okay, so let me draw it again for you. So this was the our UDL. Now we need to find the value of MQ and SQ. So SQ will be simply the shear force. So we will have an upward load here, upward reaction here, and what will be the value of that reaction? It will be 20 multiplied by 8, right? Why 20 multiplied by 8? Because we need to satisfy the vertical equilibrium. Now for this beam, the vertical equilibrium is satisfied, right? The total downward load is 160 kilonewton and total upward load is also 160 kilonewton. So vertical load is satisfied. The second thing is moment at Q. So moment at Q will be equal to load multiplied by distance. So what is the total load? Total load is 20. Total load is 20 multiplied by 8, right? And the distance is the distance between this support and the center of CG of this load, which is 4 meter, right? So moment will be 20 multiplied by 8, that is total load, multiplied by distance between the support and the CG of this load, which is this. So finally it is also coming out to be 640 Newton meter. 640 Newton. Very, very simple, right? And it looks like big problem, but it's a 2 mark question and very simple. And the third thing is, in the third question, they are just ask here the very very simple again. There is only one load, which is 640 Newton meter applied here, and we need to draw the free body diagram. So it is, if it is 640, then here it will also be 640. Since there is no vertical load applied, so there will be no reaction here. So reaction will be 0 at the support, because there is no applied vertical load here. So here the SR is 0. Okay, the shear force at R is 0 and moment is 640 Newton meter. So for all the three cases, we are getting the moment as 640 Newton meter, right? Just the shear force is changing. For first case, shear force is 80. For second case, the shear force is 160, and for the third case the shear force is 0. So if we see for SP is 80, it is 160, it is 0, and they are 640 in all the cases, right? So let's see the first option here. Option number A says that SP is less than SQ, which is right. 80 is less than 160, but it is not less than SR, because SR is 0. So this option is wrong, right? In the second option, they are saying SP is equal to SQ. SP is equal to SQ, which is not right, because SP is 80 and SQ is 160. So it is also wrong. Let's see option number 3. Option 3 says SP is less than SQ, which is right, and SQ is greater than SR. SQ is greater than SR, which is right? And it's regarding MP, regarding the bending moment, they are saying that MP equal to MQ equal to MR, which is also right. So the correct answer is option number C, right? Very simple problem, okay, as compared to the previous one we discussed. It's a very simple problem, okay. Here we are not using this I and all, okay. They are just given us to confuse us, you can say, okay. So make the problem look difficult, okay. I hope it is clear. So now we can proceed to a other problem, which is not that easy, okay. Is there any doubt? If there are any doubts, you can stop me, okay. If there are no, then I can proceed with this problem. So here there is another problem of GATE 2014, same set 2. But here we need to know one concept for solving this problem. So this was the problem. So in this problem, this is question number 33. So they are asking the bending moment at P, and they are asking us to use the moment distribution method, preferably using the moment distribution method. But I personally don't use the moment distribution method for gate, because it requires a lot of calculation. Because the same problem in which the moment distribution method can be used, the same problem can be solved using the slope deflection method. So it's better, so it's up to you which method you want to use, but I feel that a slope deflection method is easier. The moment distribution method, the only part in which they can ask questions is they have when you have to find the joint stiffness, so that part. And yeah, the recordings are available, okay. So for this type of problems, when we use the slope deflection method, and whenever there's a lot of indeterminacy, the static indeterminacy is very high, then we use the slope deflection method and the moment distribution method. For the determinate type of problems, we can solve that easily using the equilibrium equations by drawing the free body diagram and all. But whenever the static indeterminacy is very high, then we should use this slope deflection method. So here they are saying to use the moment distribution method, but I'll not use the moment distribution method, I'll use the slope deflection method, okay. But that carryover moment part and joint stiffness and distribution factor, that part you should not leave, because that they can ask separately from this moment distribution method, okay. So this is a very complicated looking frame. So they are asking to find the value of moment at P. So whenever we have this, so this is a special case. Please, if you're maintaining some diary or notes, please mark this as a special case, because yeah, so I'll discuss this, okay. So here this comes under this topic, analysis of frame with no side sway when the axis of symmetry passes through the column. So it's a special case. So in this special case, you can solve only half of the structure. Why? Because this is a case in which we have this symmetric loading, It's a symmetric structure, right? Everything is symmetric. This is 4i IC, this is also 4IC, this is IC, IC, and IC. So it's a symmetric structure. The loading is also symmetric, right? The whole W kilonewton per meter for the entire length. So whenever we have this kind of case, and whenever we have this column, which is like the center column, that passes through the axis of symmetry, then only we can use this case. Okay, so I'm discussing that case now. So we have this frame. So how will this frame deflect? So this frame deflect roughly like this under this loading. So this 90-degree angle will be maintained here. Yeah. So this 90-degree angle is also maintained here. So this, under this loading, this frame will deflect like this. So because of which, this deflection pattern, because of the symmetry, we have no rotation in this part. So we can observe that there will be no rotation in the center at this joint P. There will be no rotation here, and because since there is no rotation here, so because of which this column, this center column, it will not deform. So no deformation in this column. If you see the deformed shape also, you can see that all the other columns, this column and this column is deforming, but because of the symmetric loading and symmetric geometry, this center column will not deform. Why this is not deforming? Because there is no rotation in this P joint. Okay, so this is a special case. This case happens whenever there is a symmetric loading, the frame is symmetric, and the axis of symmetry passes through the center column. So this is a special case. Whenever we have this type of case, we can consider we can we can consider that this joint P as a fixed support. So we need not to solve the entire structure in this case. Please note this. Okay, this is a very important thing. So whenever we have this kind of condition, what we can do, we can consider this joint P here. We can consider this joint P here as a fixed support, and we will now analyze only half of the frame. Okay, let me draw it first. So this structure, the entire frame is as good as this thing. Okay, because this joint P is now acting as a fixed support. If you see, why fixed support? Because it is not, there is no rotation here, right? There is no rotation here, and there is no vertical movement here because the column is not deforming. So no rotation and no vertical or horizontal movement, because there is no sway also, because there is no horizontal movement, there is no vertical movement, and there is no rotation. So what is the this is the property of a fixed joint, right? No horizontal movement, no vertical movement, and no rotation. So this joint P is actually acting as a fixed support. So what we can do for the analysis purpose, we can just solve this half part of the structure. So the other part will be same. For example, let's call it A, this is P, and this is B. So moment A will be equal to, let's call it as, say, Q. So moment at A will be equal to moment at Q. Okay, similarly moment at B will be equal to moment at S, suppose. Okay, so we just need to solve only half of the structure. So this you can note as a special case. For this type of, whenever this condition is met, you can just solve the only half part of the structure, and you will get your answer. Okay, this is a special case. You cannot do it for all the problems, right? Whenever there is a symmetry, and whenever there is a central column and axis of symmetry passes through that column, you can reduce the structure to this half structure, and you can solve this part only. Okay. Okay, I hope it is clear. So this special case they have given in this problem. You can solve the entire problem also. It's not that it is compulsory to reduce it to half of the problem, but for the ease of analysis, we can do that, because now we do not need to, solving it is a big problem, but solving this is not a big problem if we use the slope deflection method. Okay, so in this, if this kind of big frame they gave you, then you can reduce it into half. Okay, so now we'll see it has become very easy to solve now. Okay, so we will use slope deflection method, although they are telling us to use moment distribution, but I'll be using the slope deflection method. Now I do not need this big truss. I'll just use this part, half part. Okay, so these are some tricks you should, which they expect you to know. Okay, otherwise it's very difficult to solve this entire frame. Okay, now we have this 24 kilonewton per meter. This is P. Let's call it A and let's call it P. So we will solve this only. This is 4I and this is I. Right, now this simple frame we will solve using slope deflection method. So in the slope deflection method, what we do, we know, you know that, right? Slope deflection equation you must be knowing. So what we do, we find MAP. Okay, MAP, how will I find? MAP will be equal to MFAP plus 4EI theta A by L plus 2EI here for yeah, okay, I'll just write it again because it's not I, it's 4I, right? So if I want to find MAP, so I'll write MFAP, that is the fixed end moments, plus 4EI. So for this AP part, the I is 4I, right? 4EI theta A by L plus 2EI theta P by L minus 6EI delta over L square. So this is the original slope deflection equation, right? Here there is no sway, there is no settlement of support, right? So this delta term will be 0. What else will be 0? Theta P will be 0, right? Theta P term will be 0. Why? Because P is now as acting as a fixed support. So there will be no rotation here. So theta P term will be 0. So MF AP will be equal to only these two things, right? So let me write it. Now MAP will be equal to, what is the value of MFAP? MFAP is a fixed end moment, right? So the fixed end moment, this is another table which you have to remember. So whenever there's a UDL here, so we have this, we calculate this fixed end moments, right? So this is WL square by 12 in case of UDL. This is also equal to WL square by 12. So I'm taking clockwise as positive. So for AP part, it is anti-clockwise, right? This is A and this is P. So anti-clockwise for AP. So I'll write minus WL square by 12. I'm assuming that you know some basics of slope deflection equation, okay? So WL square 12 plus 16 EI theta A by L. Other than that, we do not, the other things are 0, right? So first equation is this. Now I'll find MAB. Now I'll find MAB. MAB will be equal to MFAB plus 4EI theta A by L plus 2EI theta B by L minus 6EI delta over L square. Okay, right? MFAB plus 4EI theta A by L plus 2EI theta B by L minus 6EI delta over L square. These are the basics of slope deflection equation. Now, what is 0 here? There will be no delta, right? Because there is no settlement of support here. So delta is 0. Theta A will be there, right? Theta A is there, but theta B will be 0. Why? Because B is a fixed support. So theta B is 0. So what we have? We have this. And MFAB, will there be any MFAB? No, because no loading, no external load is applied in AB part. No external load is applied here. So MFAB will also be 0 here. So now MAB will be equal to 4EI theta A by L. So this is MAB. So let me call this as equation number 2. Right? Now we have MAP and we have MAB. Now what is the thing we need to use? Now what we use after finding out the slope deflection equation, what we do use the equilibrium equation. So what is the equilibrium equation here is the moment at PA equal to 0, right? MAB plus MAP is equal to 0. That is the equilibrium equation we will use here, right? This is what we do in slope deflection method, right? So we will use this equilibrium equation MAB plus, that is the total moment at A is equal to 0. So MAB plus MAP equal to 0. So we will add 1 and 2 and we will put it to 0. So let me write that. It will be 16 EI theta A by L, 16 EI theta A by L. Yeah.
Mm,
Why we are calculating MAB and okay. So the final motive here is to calculate the value of moment at P. Okay, so they are asking the value of moment at P, but the if we write, even if I'll not write this for, say, let's say if I want to find MPA, so final motive is to find MPA, right? So what is the equation for MPA? Equation will be MFPA plus 4EI, I is 4I here, theta P over L plus 2EI theta A over L minus 6EI delta over L square, right? This is the equation for MPA. But we do not, so P is 0, but we do not know what is the value of theta A, right? Theta A we do not know. So for finding out theta A, we are using this equation. So theta A I can find using this equilibrium equation, that is MAB plus MAP equal to 0. If I solve this equation, from this equation I'll get the value of theta A, and that theta A value I'll use in this equation and I'll find the value of MPA. Okay, so you can first write the equation for MPA also, because finally what I need to find, I need to give them the value of MPA. So for MPA, if I write this equation first, I know that I do not know the value of theta A. For calculating theta A, I'm finding this. I'm using this equilibrium equation. Okay, that is MAP plus MAB equal to 0. If I use that equilibrium equation, I'll get the value of theta A. Is it clear? So finally, I need to solve this equation. Fine, Harini? Was that this your question, right? So let me find the value. So to find the value of theta A, I'm doing all this thing. So theta A, I'll use this equilibrium equation MAB plus MAP equal to 0. So this is the equilibrium equation I'm using. So MAB is 4EI theta A over L, right? And um, MAP is minus WL square by 12. So let it be, so 24 L square, that is 8 square divided by 12, right? Plus 16 EI theta A, 16 EI theta A by at 8. So I'm putting the value of lengths also here. So here it will be 6. So please remember that these two lengths are different. Okay, so this is 6 meter and this is 8 meter. That is why I'm writing 6 and 8. So this can be, so total equal to 0. From here, the only unknown is theta A. That is, I'll keep that EI theta A. I'll find the value of EI theta A. So if I solve it, so I'll get the value of EI theta A as, so it will be 2.667 EI theta A equal to, if I solve this part, it will be 128. Okay. So from here, I get the value of EI theta A as nearly equal to 48. Please solve it if I'm wrong. It is equal to 48. So now I know the value of EI theta A. So I'll simply put the value of EI theta A in this equation. So finally I needed to find MPa, right? That is moment at P, equal to MFPA plus 4EI 4EI theta. So A, sorry, theta P. So theta P is 0. Okay, so I'm still writing the entire equation. 2EI theta A by L minus 6EI delta over L square. This is the equation. So here delta term is 0, and what else? This P term is also 0. Why? Because theta P is 0. So MPA will be equal to, what is the value of MFPA? MFPA will be same, right? MFPA is WL square by 12, but here it is in plus WL square by 12. Why? Because it is in clockwise direction, right? So these, so MFPA is WL square by 12. So if we'll calculate it, so W is 24. What is the length? L square divided by 12 plus, say, 8 EI theta A by 8. Yeah. So equal to MPA will be equal to 128 plus EI theta A. 8 will get cancelled. EI theta A value I can put it from here. So EI theta A value I was getting as 48. So MPA will be equal to 176 kilonewton meter. So this is the final answer I was getting. Okay. So this problem, otherwise if you would use the if you not just reduce this problem like this, then it will be very difficult for you to solve, because it is a huge frame. So now after reducing it to this, so we can easily solve this problem using slope deflection method. It's a very simple problem of slope deflection method, because there is no delta, okay, and the supports are fixed. Okay, so theta A and theta P and theta B are becoming 0 in the equation. You need to have some practice of slope deflection method. Okay, so whenever there is an indeterminate uh, link for the problems, you can find in, if you go to NPTEL Gate portal, there are two sessions, like phase 1 and phase 2 sessions of live mentoring session. So in phase 2 they haven't shared the link, but in phase 1 session if you go, so there's a link of YouTube channel where you can find the previous solutions. Okay, so go to phase 1 of NPTEL live mentoring session. There you will find the recordings for every session, right? So any problem? So the answer is 176 kilonewton meter. That is option number C. Okay, very simple. This session recording I'll share in the other. So I have made one channel. So I'll share. I just upload the recordings there, and I think everyone else. Like everyone else from civil has made one channel, so you can find the link of all the channels there only. That phase 1, if you go to that portal now, so just check that phase 1 session, so they'll find the link for their channels and you can check. Can it be shared here? Let me check. Okay. So any problem in this thing? I'll check the link for the switch channel. Yeah, just see if it is working or not. Okay, this is the link for the live session recordings, but we have also recorded each and every question separately, and that you can find in video solutions, but I think that will be available after some time. This, okay. Any other question regarding this thing? uh, this is whatever I have discussed today. Okay, please practice, okay, because knowing the things is different and practicing is entirely different, because applying the things and getting the answer is an entirely different thing. Okay, you must be knowing slope deflection method, you must be knowing the deflection formulas, but applying it is a very entirely different process. Okay, if there are no doubts, I'll close the session for today. It's almost 5. Okay. If you have some doubts, you can. Okay, so you can, for practice, you can note this questions. So it's also very nice question from GATE 2016, set 2. So if you want, if you can click the picture of this question. So I've made a video solution for this also. Okay. You can take the picture and practice for just for your practice. So the answer here is, I think answer is option number C. Let's see if you're getting the same or not. Okay, then thank you so much. If there are no doubts, I'd like to close the session for today. Thank you so much for listening. Thank you. Okay, bye.